Hi students, welcome to HSC Chemistry and Industrial Chemistry. This particular video is number 5 and today we're going to ice the equilibrium constant. Up to now we've had a look at the ways of calculating the equilibrium constant, and what we found is that the expression that we've been using can be summarized by the acronym PORC. So products divided by reactants gives us the expression for the equilibrium constant. But so far, we've looked at examples that have involved either concentrations we've been given, or simply we've just tried to identify or work out the expression based on the equation. But most of the questions that you get and the questions that you're most likely to get in the HSC are probably not going to be that straightforward. They're going to be a little bit more challenging. So let's have a look at a more common type of example that you're more likely to get. So here's an example of an equilibrium. This is an equilibrium involving nitrogen dioxide, a very important gas that contributes to acid rain, one of the NOx compounds that we were talking about in the acidic environment. And it forms an equilibrium with dinitrogen tetroxide, this one. The information that we get often looks like this. 2 moles of dinitrogen tetroxide is placed in a previously empty 0.5 litre container. The system was allowed to come to equilibrium, and the concentration at equilibrium for the dinitrogen tetroxide was measured to be 3.2 moles per litre. And our job is to calculate the equilibrium constant for this reaction. Now the problem with this is that we know that the equilibrium constant is concentration of products. Sorry, I'm going to just get rid of that a second. Concentration of products over concentration of reactants. Now, we know the concentration of the product is right here, so we can pop that one, sorry, that's the concentration of the reactant, so we can pop that right here. But we don't know what the concentration of the product is. That's a bit more of a problem, and it's not obvious from the question either. So we're going to need a slightly different method if we're going to solve this particular problem. So let's start with a new slide and summarize this information. So the key points are, here is the equation. We start with 2 moles of dinitrogen tetroxide in a 0.5 litre container. And we know that at equilibrium, the concentration of the dinitrogen tetroxide is 3.2 moles per litre. Because the key to the expression is going to be equal to concentration of the products, which in this case is NO2 squared, over the concentration of N2O4, that is our expression for the equilibrium constant. We can put this value directly in. We already know what it is, but we don't know what this one is. This is a mystery. We've got to work it out. So the easiest way to work it out is to use the ICE method. The ICE method relies on the fact that we need, first of all, the mole ratio, and the mole ratio here is 1 to 2. The concentrations that we get are related to the mole ratios. So we know that the concentration initially must be, for the dinitrogen tetroxide, concentration, remember, is number of moles over volume. So the initial number of moles is 2, and the volume is 0.5, so that's 2 on 0.5, which is equal to 4 moles per litre. Okay, so the initial concentration of our N2O4 is 4. The initial concentration of our NO2 is 0. It's an empty container, and all we do is put in some N2O4. So there's nothing, no product at the beginning. The next thing we want to do is we want to look at the change. How does it change through this reaction until it reaches equilibrium? Now, sometimes you'll know the change and you can put them directly in here and here. Other times you won't. In this case, we don't. We know what the concentration of the N2O4 at equilibrium is. It's 3.2. Now, given that the container is exactly the same in each case, we can kind of work out how much of the N2O4 has actually reacted. Given that the container here is still 0.5, that doesn't change, number of moles is equal to concentration times volume. So the number of moles is 3.2 times 0.5, which is 1.6. So we have 1.6 moles of N2O4 remaining at the end. What that means is we must have, therefore, 0.4 moles have reacted. So 0.4 divided by 0.5 means that the change in the concentration is 0.8. And we kind of expect that because the volume is going to be a constant all the way through here. So you'll see these values kind of line up with each other. So therefore, the change that we have in N2O4 is the 0.8. Now we need our mole ratio because the change is how much of the N2O4 reacted. And we know because the ratio is 1 to 2 that there must be 1.6 over here. Now that 1.6 comes from 0.4 moles reacting, which gives us 0.8 moles of NO2 produced, NO2, and therefore 0.8 on 0.5 is equal to 1.6. So 1.6 is the concentration of the moles per litre of the NO2. Now, if the reactants get subtracted, 4 minus 0.8 is equal to 3.2, but the products get added. We add the products together to give us our total. So the concentration equilibrium, therefore, must be 1.6 moles per litre. We can now do our calculation. So this is equal to 3.2 squared divided by 1.6. And if I get my calculator out and I have a look at that, I can go 3.2 squared divided by 1.6, and I get a value of 6.4. So therefore, the equilibrium constant in this situation has a value of 6.4. Thanks for watching.